racing across Italy at 300 kilometers per hour. A $38 million super machine. The Italians call it the Ferrari train.
It's a very big challenge running at this speed. Everything has to be designed properly.
The AGV is one of the world's fastest passenger services. What makes it so quick? And what stops it from hurtling off the track as it speeds passengers from Milan to Rome?
I'm traveling at 300 kilometers per hour. It's quite impressive.
We unlock the engineering secrets that help this high-speed train reach its destination on time. From the intelligent rooftop power supply that feeds this beast with 25,000 volts of electricity, to the innovative electric motors that thrust it up the steepest inclines, to reveal what it takes to build the ultimate super train. Italy, a nation of 60 million people, all in a rush to get somewhere. Few places are busier than the city of Milan, Italy's premier business hub. More than 320,000 people a day travel through Milan's central station. They need fast, reliable links to industrial cities in the north and Rome, Italy's capital, to the south. This is the machine they rely on to keep their day on track. The AGV. Its operational speed is capped at 300 kilometers per hour. But its max speed of 360 kilometers per hour makes it the fastest passenger train in Europe. Each one costs $38 million to build. The company that runs the train, Italo, operates a fleet that services 25 Italian cities. It runs an average of 54 services between Milan and Rome each day. A high-tech control center guides these advanced trains along the tracks, while engineers work 24/7 to keep them maintained. Italo's aim is to shuttle passengers to their destination as quickly as possible. To achieve this, the AGV train is built with innovative technology hidden under the hood to help speed it between cities. Electric motors with more power than a Formula One race car drive the train up inclines at full speed. A network of intelligent cables channel 25,000 volts into the AGV's power system. Ingenious friction-boosting technology helps the train maintain its grip on the wet and greasy tracks. All these elements combine to make the AGV the ultimate high-speed train. Today, the man at the controls of this super train is driver Dennis Laraya. The time is 7:53 a.m. Dennis has 35 minutes to complete his pre-flight checks.
Adesso sto facendo la prova del freno. Adesso questa è l'area nella condotta generale. Adesso è intercettato, bisogna aspettare un minuto per vedere che non perde, che non vada giù.
His mission today is to safely transport 460 passengers, 567 kilometers, from Milan to Rome in 3 hours and 30 minutes.
Avere tante persone sopra è comunque una responsabilità. È una bella motivazione per me.
failure means more than dented pride. Retaining the company's place in Italy's transport market relies on delivering a first-class service. Breakdowns, late arrivals, an uncomfortable ride all risk damaging the operator's reputation with passengers. It's critical Dennis gets his train to Rome on time. But his machine must cover nearly 600 kilometers of challenging track to reach its destination. Dennis must guide the train along a high-speed line, through the suburbs of Milan and across northern Italy, before stopping at Reggio Emilia and Bologna. The route crosses the Apennines and speeds through tunnels, stopping in Florence, before negotiating the web of suburban train lines that lie north of Rome, to reach Rome Central Station 3 hours, 30 minutes after leaving Milan. 8:09 a.m. Hundreds of passengers on Milan Central's busy concourse file onto platform 6 and board Dennis's train. The interior is designed to make their 3.5-hour journey as comfortable as possible. All 462 seats on board are made from leather. Each of the carriage's windows are 15% larger than on standard commuter services. Shock absorbers between the wheels and carriages reduce vibration. And the Italo looks fast. Owing to its red livery, the AGV is dubbed the Ferrari train. 8:12 a.m. Some 600 kilometers south in Rome, Italo's control room tracks the position of every AGV. Operations Director Sofia Appadula must ensure every train is ready for dispatch.
99:15 macchina.
Siete pronti per la partenza?
Siamo pronti.
Mi confermate il binario numero 6? Sì? A tra poco, grazie.
Ok, a dopo, ciao.
In Milan, the train manager closes the doors. Dennis receives the all clear to proceed.
We're ready.
The train departs on time at 8:35 a.m. As the onboard crew serve passengers breakfast, Dennis turns up power on the train's 10 electric motors. This is a machine that is built to go fast. With a top operational speed of 300 kilometers an hour, it's one of Europe's quickest passenger trains. And everybody on board expects it to live up to that promise.
Being on time, it's fundamental in my work because we have several meetings to attend like every day. So being late at just one of them means being late at every single meeting after it.
The first challenge for Dennis is to keep the train running fast along all sections of the route to Rome. This will be no simple task. Long sections of track climb hills. These inclines can slow down traditional trains. Many older passenger trains are pulled by a single locomotive at the front, or pushed and pulled at the same time, with a second locomotive adding power from the rear. This standard configuration is fast on the flat, but can rapidly lose speed up hills. When climbing inclines, carriages in the middle lose forward momentum and pull back on the locomotive. This slows the train. When the locomotives increase their power and accelerate, the lagging carriages are brought back up to speed. But the train loses valuable time. The engineers who built this super train designed an ingenious solution to help power this machine up inclines. This depot in southern Italy is where workers maintain Italo's 25-strong fleet of AGVs. Here they strip off a train's red coat to run regular checks under the hood. Francesco Vidanza leads the team responsible for keeping every Italo train running. A critical inspection of the AGV's sets of wheels, called bogies, reveals the machine's secret for staying fast.
This is a powerful motor bogie from the AGV. You can see the two big motors. They're a permanent magnet motor, very powerful, but very little.
Engineers drop the traditional two-locomotive design and decide to turn carriages into locomotives to maintain this machine's momentum up inclines. They fit a pair of innovative motors to 5 of the train's bogies. Each motor has more horsepower than a Formula One race car. The system is called distributed power. Distributed power spreads out the AGV's thrust along the length of the train. This allows the train to maintain a constant speed, as none of its carriages will lose momentum and drag the AGV back when going uphill. Each of the bogie's motors drive a pair of the train's wheels. More wheels under power means motorized carriages pull their own weight, boosting the train up inclines with no drop in speed. So the AGV stays fast along high-speed sections of track. Train driver Dennis puts the pedal to the metal. He accelerates train and passengers up to the top speed of 300 kilometers per hour.
Being this fast and sitting on a chair and then traveling at 300 kilometers per hour, it's quite impressive.
30 kilometers into the journey, the train is right on schedule.
Treno sta viaggiando in orario, non ha problemi, quindi sta andando tutto regolarmente.
To reach Rome on time, Dennis must keep the 423-ton train close to full speed. But this is a challenge. What technology keeps the AGV fed with 25,000 volts of electricity? And what is this train's secret for staying on the rails? In northern Italy, the Italo AGV high-speed train is nearly a quarter of the way into its 600-kilometer journey from Milan to Rome. The 460 passengers on board need to arrive in Italy's capital on time. The machine's reputation rests on the train reaching its destination in 3 hours 30 minutes. 150 kilometers into the journey, driver Dennis must make a stop at Reggio Emilia. It's the job of train manager Angelo Pansera to get 70 new passengers on board within 2 minutes. But there's a problem.
Indications in the platform are not correct.
The station's monitors are displaying the carriage's numbers the wrong way round.
Because we have coach number 11 that way and not coach number 1 as it is written on the monitors.
Confused passengers struggle to find their seats. The clock is ticking.
They have to correct now to help the passengers to their correct coach. He's ready, we can go.
With the passengers finally boarded, Dennis powers his super train towards Rome.
Grazie. Buongiorno. Grazie.
But the delay has pushed it 2 minutes behind schedule. For Dennis's AGV to pick up the pace and reach Rome on time, the train must be fed with a reliable supply of electric power. The AGV is just one in a long line of pioneering trains using revolutionary power systems to push the limits of speed even faster. Back in the late 1930s, trains powered by steam first break the 200 kilometers per hour barrier. Almost 4 decades later, diesel trains, like Britain's Intercity 125, hit over 240 kilometers per hour. In 1981, the electric TGV achieved speeds in excess of 300 kilometers per hour on a new high-speed track. Electric trains win out against diesel and steam in the speed stakes because they're lighter. Their engines take up less space and they carry no fuel on board. The AGV's lifeblood is 25,000 volts of electricity. It passes through overhead cables that are strung above the track. The electricity powers the train's 10 motors and all essential onboard systems. Electricity flows from the cables to the train through steel arms called pantographs. Keeping the pantograph in contact with the cable whilst traveling at 300 kilometers per hour is a huge engineering challenge. The connection between the cables and pantographs must be perfect. Small bumps in the track and tiny changes in the height of the cable could vary the distance between the train and its power source. If the pantograph presses too hard or is misaligned with the cables, it could damage valuable infrastructure or destroy the pantograph itself. If the pantograph loses contact, electricity could arc across the gap between the conductor and the cable. This could potentially trigger a fire and endanger the crew and passengers. This footage from another train shows what can happen when a pantograph malfunctions. The steel arm disintegrates and brings down overhead cables, resulting in costly damage to critical infrastructure. Sometimes bad weather, such as ice, prevents a perfect connection and electricity arcs between pantograph and cable. In extreme circumstances, electrical arcing can be dangerous. This footage shows how it can set train carriages on fire. To make sure the pantographs on Dennis's train keep in perfect contact, the AGV's engineers build a simple but ingenious solution into this machine. The key to the pantograph maintaining exactly the right contact with the overhead wires is hidden inside its base. A pneumatic cylinder moves the pantograph's steel arm up and down. The system is controlled by a computer. It intelligently adjusts the pantograph's position relative to the cable. To ensure the articulated arm doesn't crash into or pull away from the train's source of electricity. The pantograph's pneumatic cylinders guarantee Dennis's train has a safe and constant power supply. But they can't prevent everyday wear and tear. Friction with the overhead cable degrades the pantograph over time. This can increase the danger of mechanical breakdown and destroy any chance of Dennis's train reaching Rome on time. Italo's fleet of machines undergo regular checks here at this maintenance depot in southern Italy to ensure all the train's pantographs are in full working order. Engineer Francesco Fidanza must protect his team from being fried by 25,000 volts of electricity as they gear up for today's inspection.
Francesco is applying the lockers on this box that contains the key to power on the train. so no one can take the key while the locker is installed. This is a safety rule that we have to strictly follow in order to be safe on train.
With the train locked down, the maintenance crew get busy. This 145-centimeter long strip of graphite, fixed to the leading edge of the pantograph, is the train's secret to beating damage caused by friction. Graphite is heat-resistant and conducts electricity. The strip wears away, protecting both the overhead cables and the pantograph's metal frame from damage. Every 7,500 kilometers, engineers check the graphite strips are thick enough to be safe. If they're too thin, there's the possibility they could damage power lines and start a fire.
By measuring the thickness, we are able to foresee if the pantograph is good or not to continue the commercial service. Here we have 25, so at least we are okay for 30,000 miles.
The maintenance crew grinds down the strip's rough edges to improve contact with the cables before the train leaves the depot to re-enter service. It's the graphite strips built into the AGV that means Dennis can draw down 7,500 kilowatts of electricity into his train's 10 motors and power his passengers towards Rome at 300 kilometers per hour. Up ahead, a new challenge awaits Dennis's train. The Apennine Mountains. Here, the track bends around tight corners. The terrain is uneven, and passing over numerous bridges and viaducts could make the journey very bumpy. How does this super train beat topography and uneven track to guarantee a smooth ride? And what's its engineering secret for staying on the rails when traveling at full speed? In Italy, the AGV train is 200 kilometers into its 600-kilometer journey from Milan to Rome. The passengers on board expect to reach their destination on time. The AGV's operator, Italo, aims to shuttle trains between cities as quickly as possible. To deliver on that, this machine is built for one thing: speed. Paolo Belforte was part of the team that designed Europe's fastest passenger train.
Very big challenge running at this speed. Everything has to be designed properly.
The ultimate fast passenger train was born in one of the world's most advanced train construction companies. French manufacturer Alstom built state-of-the-art locomotives and carriages at 30 production sites worldwide. To make their trains shells, robots cut 3,800 square meters of paneling from sheets of super-thin aluminium. The metal's light weight makes the trains fast. The wheels for the carriages are made from specially hardened steel, tough enough to withstand spinning at 1,800 RPM for hours at a time. A team of 450 workers then assemble the thousands of components needed to make each train. 3 kilometers of pipes and ducts, 300 kilometers of electric cables, 690 kilos of paint.
I'm very proud of being traveling on this train. When you start from scratch, you always see drawing and you can imagine what it will be, but you never know. And seeing this machine working properly with the right comfort and full of passenger is a very big satisfaction at the end.
220 kilometers from Rome, Dennis's train is running 2 minutes behind schedule. The journey up ahead is far from straightforward. The track through the Apennine foothills twists and turns around the hilly terrain. It's critical the train stays on the rails around every bend. Leaving the track at high speed could have devastating consequences. The 24th of July, 2013. This Alvia train enters a tight bend at more than twice the 80 km/h speed limit. The derailment near Santiago de Compostela, Spain, reportedly kills 80 people and injures 144. Investigators conclude the train's high speed caused the crash. To prevent disasters like this happening to Italo's AGV, engineers fit the train with an auto speed limiter. If a driver attempts to go over the limit, the train takes over and applies the brakes automatically to slow the machine down to the correct speed. Secure on the rails, the AGV journeys safely towards the Apennines. Dennis's train must cross the numerous bridges and viaducts that span the mountainous terrain here. For passengers traveling aboard a high-speed train, these structures have the potential to transform their journey into a roller coaster ride. All cross-country trains travel on rails laid onto sleepers. These sleepers are often embedded in a layer of rough stones that run on top of an earth embankment. Over time, small movements in the soil beds down the track. But where the track crosses viaducts and bridges, the sleepers can be fixed to metal and concrete structures. Small bumps can form in the track at the transition points between soft embankment and rigid bridge. These bumps won't derail the train, but at 300 km/h, they can make passengers very uncomfortable. Italo's reputation depends on giving everybody on board a comfortable ride through all stages of the journey. To beat the bumps, engineers build a two-layer solution into the train's bogies. Detaching a bogie from its carriage reveals the secret to a smooth ride. Layer 1. 4 24-centimeter-long steel coil springs. Layer 2. A set of hydraulic piston dampeners mounted on the bogie's side. And a pair of bags made from tough rubber. These sit directly beneath the train's carriages. The layers work together to iron out jolts and shakes. The coil springs compress to absorb the impact of the bogie's wheels hitting bumps on the track. Pistons inside the hydraulic dampeners soak up jerky sideways movements to keep the train's wheels on the rails. The inflatable bags adjust the level of cushioning depending on the number of passengers on board the AGV. Thanks to its ingenious suspension, passengers on this train enjoy the most comfortable of rides. The silky smooth suspension allows Dennis to keep his train close to maximum speed. He claws back the time lost stopping in Reggio Emilia. But up ahead lies a challenge that threatens to push the train behind schedule again. How does this super train blast through tunnels at 300 km/h without blowing its passengers' eardrums? And what stops its wheels spinning on the slippery track? The AGV is nearly halfway into its 600-kilometer journey from Milan to Rome. The train is right on schedule as it speeds passengers through the Apennine Mountains. Up front, driver Dennis guides the train around bends at 300 km/h. Traveling this fast leaves little time to react if he needs to make an emergency stop. To keep both the driver and passengers safe in the event of a collision, engineers build an innovative protection system into the train.
This train can run up to 300 km per hour, and in case of accident, you have to absorb a lot of energy.
The nose is this train's first line of defense. Inside are 3 layers of protection. A piston for absorbing extreme impacts at the front. Behind that, a steel plate with 5 crumple zones. And a crash-proof driver's cage made from high-density steel.
Driver feel very safe because in case of incident, this part is able to absorb all the energy and the driver cab is safe.
Crash tests show the safety system absorbs the impact of a truck traveling at 100 kilometers per hour, greatly increasing the driver's chances of surviving a crash. The AGV train is now deep in the Apennine Mountains. The fastest route through is via a series of 9 tunnels, some up to 19 kilometers long. Driving a train into a tunnel at high speed is a formidable engineering challenge. Air inside a tunnel is trapped within a confined space. When a train speeds into a tunnel at 300 kilometers per hour, it compresses the air inside. Like a piston, the front of the train pushes along a cushion of air. In a split second, the air pressure in the carriages behind drops rapidly, before the air rushes back milliseconds later. This sudden pressure change could damage the most pressure-sensitive part of the passengers' bodies, their eardrums, making their journey very painful. Guaranteeing passenger comfort is critical to maintaining Italo's reputation as a premier train service. To avoid ruptured ears, driver Dennis can, at the push of a button, deploy an ingenious sealing system built into this train. Hidden inside the roof of each AGV carriage, 2 high-powered fans draw in air, pressurizing the cabins. On the driver's command before entering a tunnel, flaps concealed in the roof snap shut over the fan intakes. Rubber seals inflate around the doors, making the carriage airtight, just like an airplane, protecting the passengers' eardrums from damaging changes in pressure. As the train nears the tunnel, Dennis activates the flaps. The train is now completely sealed. It enters this 19-kilometer-long tunnel at 300 kilometers per hour. The passengers feel nothing.
It's no problem to be in the tunnel when you travel on a train. I think it's quite the same as to be outside.
After exiting the tunnel, Dennis unseals the carriages. Clear of the Apennines, his train powers on. Within 10 minutes, he arrives at the next stop, Florence. For the onward journey, Dennis will pull out of the station the same way he came in. To do this, he must switch to the driver cab at the other end of the train. The clock is ticking. The train must leave on time. With all passengers finally aboard, Dennis kicks the train into gear and accelerates out of Florence station. The AGV has just 90 minutes to reach Rome. Dennis must push the train to the max. But the stresses and strains of the task increase the risk of mechanical failure. What makes this super train strong enough to stand up to extreme punishment? And what stops its polished steel wheels from spinning out of control? The AGV is nearly 400 kilometers into its 600-kilometer journey from Milan to Rome. The reputation of the train's operator, Italo, rests with the train arriving on time. Driver Dennis once again pushes his AGV up to its top operational speed of 300 kilometers per hour. So far, it has traveled flat out for most of its journey. The longer the train travels at its highest speeds, the greater the stress on its components. At the train's top speed, the AGV's wheels and axles turn at 1,800 RPM. This huge stress, together with the extreme heating caused by friction with the track, increases the risk they could shatter, potentially leading to disaster. The 20th of December, 1984. Fire erupts from a ventilation shaft connected to Summit Hill Rail Tunnel in the United Kingdom. The cause of the blaze, a freight train hauling 13 tankers carrying more than 1 million liters of vehicle fuel. A defective axle bearing on one of the tankers breaks. It causes the train to come off the tracks and all the tankers behind to derail. The fuel ignites, causing one of the largest tunnel fires in history. Luckily, no one is killed or seriously injured. To prevent such a disaster happening to the AGV, engineers design its wheels to soak up extreme punishment. Each of the train's 48 wheels is made from a single 1.2-ton piece of steel. During forging, each wheel is quenched in liquid. The exterior cools rapidly, creating a hard surface. The core cools slowly, making it more flexible. The wheel's softer insides absorb extreme shocks and stresses. The hard exterior can pound the track for over 1 million kilometers. The wheels and axles are tough, but they can develop microscopic fractures that weaken the metal to the point it breaks apart. Regular checkups are critical to identify potentially dangerous defects before it's too late. The cracks are too small to see with a human eye. So engineers use ultrasonic testing to look inside the metal.
Con questa macchina ultrasuoni noi riusciamo a capire se ci sono delle possibili indicazioni che ci indicano delle cricche sul materiale, quindi con possibili conseguenze disastrose per il servizio. Questa è un'attività che noi ripetiamo ogni 375.000 km.
This scanner sends a sound wave into a train's axle. The strength of the sound's reflection alerts engineers if there's a dangerous defect hidden inside. The team immediately replace all damaged wheels and axles. super tough wheels give Dennis the confidence to push on to Rome at top speed. The Italian capital is still 100 kilometers away, and the clock is ticking. Commuters on board expect to reach their destination in 30 minutes. But ahead lies a challenge that threatens to push the train behind schedule. Hazards on the line itself. Mud, leaves, and other organic matter on the metal tracks can make them slippery, causing the AGV's wheels to lose grip. A lack of grip between the wheels and the track could turn into a skid. This could greatly increase the stopping distance of the train in an emergency. In the worst case, the skid could cause a train to come off the rails. To beat the skid, engineers build 4 special boxes into the nose of the train. Combined, they hold 80 kilograms of coarse sand. A pipe connects the box to an outlet directly in front of the lead wheels. At the press of a button, the train's driver can release the sand onto the track. When pushing hard to beat the clock, this simple system can make all the difference in slippery conditions. Sensors mounted in the bogies monitor the rotation of the wheels on each axle. If one axle spins faster than the others, it means one of the wheels is slipping. To prevent loss of traction, the driver releases sand onto the track to help give the wheels extra grip. The sand has a lot more friction than the steel rails. Although only a few millimeters deep, the sand layer breaks the erratic spin of the slipping wheel, bringing it back under control so that it regains traction. After nearly 550 kilometers, Rome Central Station is in sight. Dennis's AGV must arrive on schedule, but one final obstacle could wreck his chances. Up ahead, the train's specially built high-speed track crosses a network of suburban rail lines. What technology stops this super-fast train from getting stuck behind slow commuter services? And will this train make it to Rome on time? One of Europe's fastest passenger trains, the AGV, is now just 20 kilometers from its destination, Rome Central Station. But crisscrossing commuter lines make this the slowest section of the entire route. Operations Director Sofia Apadula monitors the train's progress from Italo's command center.
Approaching to Rome, trains leave the high-speed line and they travel on the same tracks where there are also local trains.
After speeding through Italy at 300 kilometers per hour, getting bogged down in this congestion on the outskirts of Rome will blow any chance the train has of reaching its destination on time. Sophia and her colleagues access a system called Communication-Based Train Control to monitor in real time the precise location of every Italo train in Italy. Its primary purpose is to tell an infrastructure manager the status of essential systems such as signals, electricity cables, and junctions. When it shows congestion lies ahead for time-critical services, Sophia can request the track be cleared of slower traffic.
Sometimes we have, like in this case, to move the train on that way. According to the rail infrastructure manager, we can pull this train out of the high-speed line before in order to get the train to the main station on time.
99,15 macchina.
Sì, il gestore mi dice che la linea è pulita e potete procedere. Siamo a posto. Grazie.
With the track ahead clear, Dennis's train has every chance of arriving on schedule.
With Italo, I must admit that the train are always on time.
It's a very good service. I don't have any problem with so good experiences.
Finally, after 3 hours and 30 minutes, the train pulls into Rome station.
We've just arrived to Roma Termini. The train is on time. We've done a good job today.
The AGV's reputation for super speed and punctuality remains intact.
Siamo arrivati a Roma in orario. Io ho finito il turno, per adesso.
Today, Dennis's train accomplished its mission. It's all thanks to 5 engineering marvels built into its sleek frame that help make it one of the world's ultimate passenger trains. Intelligent electric motors maintain the train's speed up any incline. Reactive pantographs safely channel 25,000 volts from live overhead cables. Sophisticated multi-layered suspension smooths the ride. An ingenious pressurized sealing system protects passengers' eardrums. Sandboxes beat greasy track and stop wheels slipping. This is a train that's fast and engineered for both safety and passenger comfort. The Italo AGV is built to be the ultimate in its class.